Welcome back. In the previous video, we combined Perlin noise and ridge noise to create a mountain landscape. But when you look at the terrain, something still feels missing, doesn't it? The overall shape is there, the mountain forms are there, but it lacks that natural look you would expect from a real mountain, one that has been shaped by water and wind over many years. The surface still feels a little too smooth, too symmetrical, and a little too computer-generated. I right-click on an empty area in the graph, type hydraulic into the search box, and the hydraulic erosion node appears right away. I select it. Now let's connect it. Pay attention to the placement here. This node goes between the output of the height map blend node and the height map to terrain node. In other words, first we blend the Perlin noise and ridge noise together, then we send that result into the erosion node, and finally we write the eroded height map back to the terrain. Let's select the hydraulic erosion node and examine its settings in the inspector. There are quite a few parameters here at first glance, but don't let that intimidate you. We'll break them down one by one and see how each setting affects the final result. First, we have Droplet Count. This controls how many virtual raindrops will be simulated during the erosion process. By default, it's set to 50,000. The higher this value is, the more detailed and natural the erosion pattern becomes. However, it also increases the computation time. For this example, we'll increase it to 150,000 to create a richer and more detailed erosion effect. Next, we have Max Droplet Lifetime. This determines how many simulation steps a droplet can take as it travels across the terrain. By default, it's set to 64, but we'll increase it to 90. This allows the droplets to travel farther, carving longer channels and creating deeper valleys throughout the landscape. Next is Inertia. This controls how strongly a droplet maintains its current direction as it moves across the terrain. A higher inertia value causes droplets to follow smoother, straighter paths, resulting in more pronounced erosion channels. A lower inertia value makes droplets respond more quickly to local changes in the terrain, producing a more irregular and fragmented erosion pattern. For this example, we'll set it to 0.08. Next, we have Sediment Capacity. This determines how much material a droplet can carry at any given time. Higher values allow droplets to transport more sediment, leading to more aggressive erosion and deeper valleys. For this example, we'll leave it at 5. Next is Gravity. This controls the influence of gravity on the simulated droplets. In practice, it affects how quickly water accelerates as it flows downhill across the terrain. For this example, we'll set it to 4.5. Next, we have Erode Speed. This controls how quickly material is removed from the terrain during the erosion process. Higher values result in stronger and more aggressive erosion. For this example, we'll set it to 0.26. Next is Deposit Speed. This controls how quickly transported sediment is deposited back onto the terrain. It has a direct impact on how much material accumulates in valleys and low-lying areas. For this example, we'll leave it at 0.3. Next, we have Evaporate Speed. This controls how quickly the simulated droplets evaporate as they travel across the terrain. Higher values cause droplets to disappear sooner, resulting in shallower and more localized erosion. Lower values allow droplets to travel for longer distances, carving deeper channels and more pronounced erosion features. For this example, we'll set it to 0.08. Next is Erosion Radius. This determines the area of terrain affected by each droplet as it erodes the surface. Larger values spread the erosion effect over a wider area, resulting in smoother and broader terrain features. For this example, we'll set it to 4 to give each droplet a slightly larger area of influence. With all the parameters configured, it's time to click Generate and see what kind of landscape the erosion simulation creates. The difference is immediately noticeable. The previous terrain looked smooth and somewhat symmetrical. But now, take a look at the surface. Small erosion channels have formed along the upper slopes, subtle depressions have appeared, and sediment has accumulated in lower areas. The terrain now looks as if it has been shaped by flowing water over millions of years. Let's take a closer look. The erosion channels along the slopes feel much more believable. The major ridge formations are still intact, but the surface now has far more detail, complexity, and natural variation. Overall, the landscape feels significantly more organic and realistic. Now let's see how these parameters affect the terrain. We can increase the droplet count even further. Right now, I'm testing with 180,000 droplets. After generating, you can see that the erosion channels become denser and more detailed, almost as if the terrain has experienced a much heavier period of rainfall. Let's also look at the effect of lifetime. Long-lived droplets travel farther across the terrain, carving longer valleys and more extensive drainage networks. Short-lived droplets, on the other hand, only affect the surface locally, producing a much subtler erosion effect. The result you're seeing now is generated in well under 5 seconds. In fact, you can see values such as 283 milliseconds and 295 milliseconds in the console. This is where PCGForge's incremental caching system comes into play. Nodes that haven't changed are not recalculated. Only the part of the graph affected by your modification, in this case the erosion parameters, is processed again. This allows you to iterate quickly and experiment with different settings without having to regenerate the entire graph every time. So, what did we learn in this video? To add a significant amount of realism to a terrain, we only needed a single node, the Hydraulic Erosion Node. Noise algorithms provide the mathematical foundation in large-scale landforms, but once we add erosion simulation on top of them, the terrain begins to resemble a real landscape shaped by natural processes. In the next video, we'll explore the Thermal Erosion Node. We'll use it to stabilize ridges and hill formations, simulate the effects of freeze-thaw weathering, and soften some of the sharper features left behind by hydraulic erosion. See you in the next video.